Today we will start design approach to the processor. It's called pipeline design, and that is the approach which is followed in most modern processors. The idea of pipeline here is similar to an assembly line, where you have a series of operations to be performed, and there is a set sequence of jobs which flow through various stages or various stations. So imagine that you have a simple task of, let's say, doing bottling. So there may be many steps involved: cleaning the bottle, filling the material, capping it, putting the label and sealing it, and so on. So it is not that the entire assembly line resources are dedicated for one bottle and then you move to next bottle and so on. So as one bottle goes through one stage to other stage to next stage, there are other bottle which follow after it on a conveyor belt or some similar mechanism. So we will talk of something similar here, where sequence of instructions will flow through series of stages of hardware data path, and there will be many instructions at any time in flight throughout the data path. So first of all, we will discuss why we want to do the pipelining, why we want to go for this kind of design, what is its influence on the clock period and CPI, or cycles per instruction. We will then briefly look at the data path design for this approach, how we represent it graphically for the purpose of analyzing the operation. Then finally, we look at the problem which we face while trying to do so. Okay. It ideally looks all right, but when you look through the details, there are some difficulties, and that prevent us from achieving perfectly what we want to achieve. So recall that we had started with a single cycle data path design, where once you start with an address in PC, the information flows through various stages within a cycle, and the instruction completes at the end of the cycle. So for example, here starting with address of the instruction in PC, the instruction is fetched, the operands are fetched, operation is performed in ALU, if necessary memory is accessed, if required results are written. All that happens in a cycle. Meanwhile, if required, new address for the next instruction will be calculated. So we had a couple of problems with this, particularly there was a difficulty in achieving a fast clock rate, because the slowest instruction here pulls down the clock frequency. Okay. And secondly, resource utilization is poor, although if you look at, let's say, adder, once the information has flown through it, the adder is not doing anything useful, but adder remains tied up, adder is engaged for the entire duration. So in fact, all resources appear to be busy all through, whether a change is occurring in them or not. Okay. So once, let us say, a new address comes up for register file, the operands are brought out on the output of register file, but now that remains static throughout the rest of the cycle, and we in a way are tying up all the resources all the time. And of course, there is a fundamental limitation of this approach, that there are many instructions which just cannot be executed in this kind of approach, particularly when instructions involve inherently sequential operations. We have taken some examples of such instructions in the tutorials. So with that problem in mind, we move towards a multi-cycle data path design, and here I am redrawing that same design, except that just to make things look little simpler, I have excluded the J instruction or the jump instruction. So some bit concatenation which is happening for jump address calculation is omitted. So here what we had done was, step by step we did 2-3 things. One thing was that we tried to economize on the resources wherever it was possible to merge, we did that. Then we introduced registers to make sure that resources after one cycle become free for next operation. So, registers are actually to store the value, so that the resource becomes free. So, the same data path after merging memories and eliminating adder is shown here. We had then introduced registers, so that the action of one cycle gets isolated from next cycle, and finally introduce multiplexers to complete the data path. Again, I have omitted jump instruction. So, now as we have come from single cycle data path to multi-cycle data path, what we have got is a much faster clock. Okay. A clock now clock period needs to accommodate not entire operation of one instruction, but one specific micro operation, right. So, now let us look at things little more abstractly. This is I am omitting now, I am going to omit the registers and multiplexer, just show main key resources and their interconnections. So, basically all multiplexer and registers would be gone. We have instruction memory, register file, ALU. I think I will take out this. So, register file, ALU, data memory and 2 adders, whereas in the multi-cycle data path we have a single memory, register file and ALU, and registers isolating these. So, now let us look at a more precise comparison of these two. In single cycle design, each resource is tied up for the entire duration of the instruction execution, whereas in multi-cycle design, resource utilization is better. A resource which is utilized in cycle T of instruction I is available again for cycle T plus 1 for the same instruction I. Okay. So, a given resource can do whatever is required in different cycles for the same instruction. In pipeline design, what we will try to achieve is something different, that a resource which is utilized in, let us say, cycle T for instruction I is after that free for the cycle T of instruction I plus 1. Okay. That means, if addition is done in third cycle of one instruction, that adder will do same third cycle addition for the next instruction. Okay. So, here by T I do not mean an absolute time, but I mean the second cycle of instruction or third cycle of instruction or fourth cycle of instruction. So, we are trying to share resources not within an instruction, but we are trying to share across the instruction. So, one instruction goes past a resource and the next instruction comes in. In terms of cycle time and CPI combination, this is how we can place 3 designs. The first design was the single cycle design, where we had a long cycle time, okay, whereas CPI was low. By definition, CPI was 1 because we are talking of a single cycle design. On the other hand, in multi cycle design, we achieved a short cycle time, right, but on the other hand the CPI went high. So, now if you recall how performance is determined, performance is related to the product of these two quantities. Okay. So, you want both these to be low, you want low CPI, possibly if you can do 1, it is very good, and also you want faster clock, short cycle time. So, basically farther away from origin you are, the worse it is, and the pipeline design actually tries to get a short cycle of the multi-cycle design and a low CPI or CPI of 1 of single cycle design. So, what it means is that every cycle, ideally in every cycle we want to push in one instruction in the pipeline, right. And in very simple case, imagine that the resources are placed in a sequence one after another, and instruction will flow through these linearly. Okay. Therefore, if there are no problems, there are actually problems which we will discuss later, but imagining that this pipeline can flow smoothly, the CPI we can achieve is 1. The clock period, on the other hand, is still dictated by one operation and not entire duration of the instruction. So, the cycle time would be more or less similar to what you get in multi-cycle design. There would be subtle differences, the two may not be exact. So, I am showing somewhat a qualitative picture and not very quantitative picture. Now, one thing we must notice is that if you focus your attention on a particular instruction, the instruction is still taking multiple cycles. Okay, instruction has to go through several stages, and it emerges or it completes its action only after multiple cycles, but the rate at which instructions are initiated, the throughput is higher. So, ultimately when you are executing large number of instructions, it is the throughput which will matter. We are not for a large program, we are not worried about how long one instruction took individually. We are worried about the rate at which instructions get executed, because that will ultimately determine the time. So, if you have of course, the number of instructions is finite, and at the end you have to wait for the last instruction to finish. You are not it is not sufficient to just worry about initiation of the last instruction. So, if let us say there are 100 instructions and each instruction has to go through 5 cycles, then the 100th instruction starts in 100th cycle, okay, and it finishes in 104th cycle. So, total number of cycles will be 104, but approximately if since you are going to have not 100, but 1000 millions of instructions, roughly speaking, the initiation rate would determine the total time. Okay. Now, how do we design a pipeline data path? You see in this picture, all that I have done is I have taken the same data path of the single cycle design. Okay. I have as I mentioned that I would take this where I am omitting the multiplexers and some small details, just try to show broadly the flow of the information. So, same diagram I have taken and introduced a couple of registers. We did introduction of registers in case of multi-cycle design, when we went from single cycle to multi-cycle design. Of course, there our attempt was twofold. We were also trying to share resources within an instruction. We are not trying to do that. By this pipelining mechanism itself, the resources will get shared across instructions. So, we are leaving the single cycle data path as it is and introducing registers. So, I have drawn these like walls, vertical walls, which are crossing all the forward going lines, right. So, everything which is cut by all lines which are cut by these vertical walls are basically passing through registers. That means, output of this gets stored, output of this gets stored, and is available in the next cycle in this stage. So, the whole data path is actually very clearly divided into stages. You can label these as IF stage, instruction fetch stage, instruction decode or register fetch stage, execution stage, memory access stage, and write back stage. So, write back is actually happening into this register file, but it is a stage which is afterwards. So, that is how I have written. And these registers which separate the stages are labeled by the two neighboring stages. For example, IF stroke ID means the register between these two stages. So, now in this most of the paths are actually forward going paths, which get broken by the registers. There are two backward going paths. Okay. One is this, the data which needs to be written back into register file. So, naturally it has to go back because it is same register file which is doing read and write, and the result of this PC address calculation, this also has to go back to PC. So, these are the two and these do cause some complications which we will see in due course of time. So, the ideal thing is that pipeline should be so called linear pipeline, in the sense that things only move forward and do not come back, because coming back in some sense is an indication of reutilization of the resource. So, for example, if let us say if we had same single memory for instruction and data, in this stage the address will have to be routed back to this memory, and then the data could be taken out further. So, that would definitely create some complications, because by the time you have reached this stage some other instructions have moved into the pipeline and there will be a conflict. We will I will precisely define this kind of conflict little later, but at the moment we assume that pipeline is by and large a linear pipeline. Okay, now there is one problem here is in terms of how we are starting the next instruction in the next cycle. Next instruction is dependent upon the next value of PC, but the way we have done is that the next address calculation is actually getting completed here, where you are ready to select between PC plus 4 and PC plus 4 plus offset, and that is happening, that is available only after, suppose this was first cycle, second cycle, third cycle. So, it is only in fourth cycle we have this value which we put back in PC. Okay. But if you do that, then you cannot really run your pipeline and keep it full. So, we need to quickly be ready with PC plus 4 in the next cycle itself, and therefore, I carry out slight modification of the data path, is that the multiplexer, of course, I am not showing multiplexer here, but the multiplexer which selects between PC plus 4 and PC plus 4 plus offset is actually placed within the first stage. So, that is very important, and the complication here is that since there are many instruction in the pipeline, there will be some instruction here and there will be another different instruction in this stage or in this stage. Okay. So, we are trying to mix up things, but at the moment let us ignore that. We will come to understand the implications of that, but right now our focus is on quickly calculating PC plus 4, and for the moment let us imagine that we do not have BEQ. Let us just turn our eyes away from that and imagine that we have instructions like load, store, add, subtract and SLT and so on, and for quite some time we do not have BEQ instruction. So, as long as we keep that away, we have a possibility of being ready with PC plus 4 in every cycle. So, therefore, this part is really now geared to pump in a new instruction every cycle. Okay, is that part clear? Okay. Now, let us try to analyze things a little bit. Okay, for that we will not carry that big diagram and I abstract it further. So, you can either show very symbolically 5 stages which we have: instruction memory, register file, ALU, data memory, and again register file. So, RF I am placing twice because there are 2 different functions being performed here. You are reading here and you are writing here. So, it is same register file, but logically I want to lay it out as a conceptually show it as a linear pipeline, or I can show in terms of actions, that the action happening here is instruction fetch, instruction decode, execute, memory access and write back. Okay. So, now I could look at this, maybe try to put multiple instructions in the pipeline and see how it happens. And there are two ways we can do it. We can, okay, yeah, before I go for that, we can show usage of different stages by different instructions by properly shading. I want to just check if these, it is very light, but are these shades visible? Yes or no? Okay. So, you would notice that these boxes I have, in some cases I have shaded, and some cases they are half shaded. Okay. So, for let us say devices like register file, if I am shading the right half, it actually means I am reading, because I am shading the active part closer to the output ports, and shading the left half means that I am indicating a write action. So, I am shading the portion close to the right port. So, similarly for memories, ALU of course gets fully utilized. So, either it is fully shaded or not shaded. In this you will see always shaded here. IM always gets shaded in the right half. DM may get shaded in the left half or right half. Okay. So, for different instructions, here add will represent that entire class. So, for load, let us see, IM is reading register file, utilizing ALU, then reading from memory, writing into register file. For store, these first three steps are same. The fourth step is that you are writing into data memory. For add instruction, memory operation is skipped and there is a bypass path. So, after that I am doing writing to register file. For BEQ, I need only first three stages. Now, also imagine that whether an instruction requires 5 stages or less, we will not worry about that part of it. So, for example, add instruction will do register writing in 5th cycle only, and therefore, we will be wasting a cycle in between as far as add instruction is concerned. And this does not bother us, because as I mentioned that what is of concern to us is the throughput. Okay. So, by trying to do register write in 4th cycle, we might create complications for instructions before or after. So, we do not do that. We have sort of fixed, as shown here, fixed what is done in which cycle and at which stage. So, write back is always 5th cycle, right, whether you need something in between or not. So, here the deviations from this are not too many, but in a realistic situation, when you have many instructions, the differences between instructions may be more varied, and therefore, you will find that in utilization of stages there may be more holes, but again this uniformity helps in organizing the pipeline. All right. So, now how do we represent execution of multiple instructions over the pipeline? There are two approaches which we can follow. One representation is that on the horizontal axis we represent time, and on the vertical axis we represent different instructions, show a sequence of instruction. Alternatively, we can show pipeline stages on the horizontal axis, and on the vertical axis we show time. So, let me illustrate both of these. So, here is the first approach. The horizontal line is the timeline now, okay, and each row would represent how an instruction is progressing. So, instruction I progresses through the 5 stages in time. Here time is in terms of clock cycles. Okay, I am not counting time in nanoseconds or microseconds, it is in terms of clock cycles. So, cycle T, it does instruction fetch, in cycle T plus 1 it does decode, and so on. It goes through the pipeline in the time cycles T to T plus 4. Next instruction enters the pipeline in time T plus 1 and leaves at T plus 5, and so on. So, you have instruction after instruction which are entering the pipeline, and you can show multiple instruction by showing them staggered in terms of their stages like this. Okay. So, now if you want to look at snapshot at a particular time, for example, let us say time t plus 3, you have instruction I in DM stage, instruction I plus 1 in ALU stage, instruction I plus 2 at RF stage, and instruction I plus 3 in IM stage. So, second representation which I mentioned will try to capture this. Okay. So, here is the pipeline. So, we are in a sense we are keeping the pipeline stationary, and we are trying to see how instructions move through those. So, at time t, these are the instructions filled in the pipeline in different stages. In the next time cycle, these instructions shift one stage right, and you have I plus 1 here, I here, and so on. So, again you can focus your attention on a particular stage, and you will see that how instructions are going past this stage in different time cycles. Okay, you can focus your attention on any of these, and you can see how instructions are flowing through each of these stages. So, basically whether we go for this representation or this representation, they are trying to capture same information just from two different angles, and the idea in any of these is to be able to see how the instructions are placed to each other relatively, because there might be some interaction which may have to take place between instructions, and for that purpose you need to see several of these together. So, now if the instructions can flow the way I have shown in last two slides, everything is wonderful, okay, and you achieve the CPI of 1. But in practice this may not always happen, okay, and there are some obstructions or hurdles in that happening. So, these hurdles can be classified into these three hazards, which are called structural hazards, data hazards, and control hazards. Structural hazards are basically resource conflicts, where two instructions are trying to utilize same resource at the same time. Okay, if one instruction is utilizing ALU in one cycle, and in the same cycle another is utilizing the register file, there is no conflict. But if something happens that two instructions want the same thing, then there is a conflict and pipeline gets choked. Why would this happen? This could happen if the pipeline is not linear pipeline. We have shown very ideal linear pipeline where nothing comes back. The only place we are coming back in our design is that we are sending the address back to PC, but that of course does not cause problem, because it is address for the new instruction and new instruction gets initiated by that. The other place is that the data which is to be written back into register file is actually coming back. Okay. So, but fortunately it does not conflict. Let us go back and see it here. For example, instruction I is writing into register file in cycle t plus 4, whereas instruction I plus 3 is reading from register file in the same cycle. But the kind of design we have assumed for register file, we have said that it can do reading and writing simultaneously. It has two read ports which will be utilized in this example by instruction I plus 3. At the same time, the write port will be accessed by instruction I. So, there is no conflict, because the resource has that ability to cater for two instructions at the same time, right. On the other hand, the way we have chosen our memory is that it can either do read or write at the same time. So therefore, trying to share DM and IM would not have worked out. For example, you would notice that in cycle t plus 3, I is using DM and I plus 3 is using IM, and if this memory is not capable of doing one read here and one read there, then there would have been a problem. If you do want to share and you can put a multi-port memory here, this could work, but practically these memories are not multi-port, and therefore it makes sense to keep this structural hazard away by having two separate memories. Okay. In real practice, you actually have a single main memory, okay, but what you have separate for instruction and data are the caches. So sometimes you may have multiple caches, so multiple level caches. The first level cache, which is closest to CPU, plays actually this role. You have separate instruction data cache there. Another situation which actually can lead to structural hazard is that if your ALU has to do very complex operations which inherently take multiple cycles. So far we have been talking of add, subtract, compare and so on, but suppose we were to extend our design to include multiply and divide. All right, we have discussed designs which are single cycle design as well as multiple cycle designs. Particularly for divider, we have it's possible to have faster divider, but let us say we know only how to divide in multiple cycles. Okay. Then a divide instruction will be in this stage, ALU stage, for several cycles, and what happens to the instruction which are following it? They will get held up. So the pipeline will see a structural hazard or a resource conflict either when two instructions are trying to utilize same resource because of non-linearity in the pipeline, or because some stages take longer and some stages take less. Because of that imbalance also, you may end up in one instruction still busy with the resource where second instruction has reached that point and is demanding the same resource. Okay. So now this is a hazard in our design. By design we have kept it out. Okay. For the subset of instruction we are working, we have a data path where there is actually no structural hazard. The data hazard, on the other hand, is not entirely a function of the hardware, but it is something inherent in the computation you are trying to do, and it comes because of dependency among the instruction. So one instruction produces a result which is required by the next instruction. So that is a fundamental computational requirement, and you cannot let one instruction go past another instruction or follow very closely another instruction because of this dependence. So only when the result has been produced it can be consumed by the other. So that is a fundamental limit, and we will see what are the implications of that. Finally, control hazards are because of break in flow of control. So you have branch instructions or jump instructions where excuse me, can you please go out of the class? I am talking to you. I notice that you are continuously speaking. No, please go out. The last category of hazard is the control hazard, which come because of branch or jump instructions where we alter the flow of control. Recall that we had made an arrangement to calculate the next instruction address PC plus 4 every cycle so that we can keep the pipeline full. But these instructions mean that you have to take a decision, and that decision may be taken in a later cycle, say third cycle for example. So till that happens, you do not know what is the next instruction to be executed, and that is again a fundamental difficulty in trying to keep the pipeline full. Okay, so elaborating further on this, the structural hazard, as I mentioned, is because of the resource conflict. So if we do not have separate instruction data memories, we will have conflict. We have deliberately retained the multiple adders which we had in the single cycle design, so that no resource conflicts arise. If you do not have that adder, many instructions would need to utilize ALU in multiple cycles, and then we will have difficulty because the way we have designed the pipeline, we want resource to be free for the next instruction. Okay. So, each instruction at the moment uses ALU at most in one cycle, right. There are instructions like jump which do not use, but others will use ALU not more than one cycle, and that is true of all the resources. And as I mentioned that ability of RF to allow read and write simultaneously keeps the structural hazard away. Okay, let us look at the impact of data hazards. So, suppose you have a sequence of instructions, load word followed by add, subtract, SLT. So, the key thing to be noticed here is that this instruction is putting something in register T1 which is utilized by instructions which are following it. Okay. Now, let us try to understand where will this value be put in T1 and where will it be utilized. So, instruction I will have this information brought from memory and put back in this register file in the time cycle. Notice that in this representation the horizontal axis is the time axis. So, this represents one particular time slot, and the data which this instruction produces is available after this cycle. Now, whereas the next instruction, which is add instruction, it would normally like to read the operands in this cycle from the register file, and this is in time, this is happening earlier. Okay. So, there is a problem here. We have to position, we have to sort of retime these things, so that the register read here of this instruction happens afterwards. Okay. So, it should actually happen after a gap of these two cycles, should happen somewhere here, right. So, whole thing has to be delayed. If you look at this, because there could be multiple instructions which are dependent, this value is being also read in instruction I plus 2, and I plus 2 is trying to read it here, and earliest it can read is here, and so on. So, I plus 3 also would need to be delayed. So, depending upon which instruction is trying to read data from which instruction, you may have to introduce delays, and the impact of these delays is that your pipeline is not full always, and the throughput rate or the CPI becomes more than 1, or throughput becomes less than 1 instruction per cycle. So, here I show how you need to stall or delay an instruction because of this hazard. So, this instruction which would have normally started here in this cycle needs to be start little late, so that register reading takes place after writing has taken place. Now, I have done something little cleverly here, that actually I am doing this reading not after this cycle, but in the same cycle. This is possible if you can do reading in the later half of the cycle and writing in the earlier half of the cycle. So, assuming that the register file is inherently little faster as compared to ALU and memories, and the time for clock cycle is dictated by the other units. For just as an example, suppose register file read write time was 1 nanosecond and ALU time was 2 nanoseconds, instruction memory and data memory access time was also 2 nanoseconds. Okay. So, then I keep a clock period of 2 nanoseconds, and within these 2 nanoseconds, as far as register file is concerned, I can spend first half of the cycle or 1 nanosecond in writing and later half in reading. Okay. So, that gives me little advantage here, and otherwise I would have to delay it by 3 cycles, and I am now managing by delay of just 2 cycles. Okay. So, this is a, if you do not do that, then there will be more delay. Okay. Now, whether we can do it or not actually depends upon the timing. For the example of timing that I chose, it is possible, it may not always be possible. So, one has to know that in general the delay would depend upon where you can schedule write and where you can schedule read. So, stalling is the simplest response to the data hazard, but it is possible to do something better. What you do is data forwarding, where we try to make the data go from one instruction to other instruction as soon as it can. So, instead of letting the data first be written into register file and then read from register file, we can create extra paths in the data path that the result of first instruction, for example, which are available after ALU cycle and are required by ALU cycle of the next instruction, are somehow passed directly. So that means here we are saying forwarding in the logical sense in terms of instruction to instruction, but in terms of data path, if you notice, what it means is that output of ALU is also being fed back to the input of ALU. Okay, it means that we would need some multiplexers to carry this additional path. All right, we will get to those details little later, but I would just like to understand, you to understand the basic idea that if we let this information be forwarded in this manner, then you notice that we do not require to stall the instruction. Okay. The action of writing it into register file will still take place, because maybe some instructions down below also need that. Okay. So, they are not immediately reading, but instruction which is following, and this would require some analysis by the hardware. The controller will basically have to see if there are two consecutive instructions of this kind, where the destination of one is the source of other, then we simply allow this to, we activate that path, right. There are many other possibilities, and in subsequent slide let me quickly show other possibilities. If the first instruction is load and the next instruction is, let us say, add, load instruction has the required value available only after the memory cycle. So, here we are forwarding from this memory cycle from data memory output to ALU input, and here you need to introduce one delay. Okay, but it is still better than having two delays. We have not eliminated the delays, but we have reduced the delays. This is another possibility. Now, here the next instruction is a store instruction. Recall that store instruction has two different uses of two registers. Okay, one register it uses for address calculation in third cycle, and another register it requires for transferring data to memory in the fourth cycle. Okay. So, in the previous two examples, in this diagram and in this diagram, the second instruction is an instruction which requires data in the third cycle. So, here I am looking at instruction which requires data in the fourth cycle. So, it is this register, SW will have another register here as part of the address specification. So, that gets utilized in third cycle, but this is utilized in fourth cycle, and we need that data here. So, whether it is add instruction, we can forward from output of this stage. It is basically the output of ALU, which will be simply just passed through this stage without any modification, will be available at end of this stage, okay, and then passed on to input of the data memory, right. And if it is a load instruction, which is the first instruction, then of course from output of data memory you can pass on to input of data memory. So, let me approximately indicate in the data path where these paths are actually. So, we talked about path going from ALU output to ALU input. So, it will not be strictly speaking ALU output immediately, but after the register. Okay. After this stage, the data is available at this point, and that is fed back and brought in through multiplexers to this input or that input of ALU, or it could be output of memory which is picked up from here brought to the input of ALUs. Okay. For store instruction, we need to bring it here either from this point or from that point. Okay. For an add instruction, let us say there is an add instruction followed by store instruction. So it is this data which was output of ALU, but it simply idled here and came here. This will be brought back to this through a multiplexer. So we will see those details little more deeply later on, but the basic idea is that we incur this additional expenditure of more paths and more multiplexers, and as a result we can possibly reduce some delays and in some case also eliminate. Okay, what happens due to branch instructions now? So as I mentioned earlier that when we talked about initiating one instruction every cycle, we said let us keep branch away. Now let us face this consequence of having branch instructions. Suppose this instruction I is a branch instruction, all right, and here if some condition is true, we are branching to some instruction L which is not consecutive instruction, it is somewhere else. So after this instruction there will be a tendency to start I plus 1 or I plus 2, okay. But the actual address is only known after this stage, okay, after you have done the comparison and you have also calculated the next address. So if the branch was to be taken, it is in this cycle that you can initiate instruction L. So now you have two choices, that either moment you notice a branch instruction, you freeze the pipeline, do not do anything, just allow that instruction to go up to a stage where decision is known and then get the next instruction and proceed. So in the process you would have lost a few cycles, but that cannot be avoided. On the other hand, you might say that okay, I'll wake up only when I know, but meanwhile let it continue with the instruction in sequence. So the hardware will pick up the next instruction because PC plus 4 is already there, start it, in the next cycle take I plus 2 instruction and push that in the pipeline, and here you realize that probably you have gone wrong, and then you abandon this, flush it out of the pipeline and start something which was actually required. Okay. So here you are doing something in anticipation. If condition turns out to be false, then you have actually utilized the cycles. If condition turns out to be true, then you did something in good faith, but now you have to abandon it. So it does not matter, all right. There is no way you can start earlier than this. So this is one particular one way. Okay. So just to revise, one was to not do anything, wait till decision is done, okay, and then start the right instruction. Okay. So whether it is the choice is between actually I plus 1 and L. So even if it is I plus 1 to be done, you start it here. The other approach says that okay, start something in anticipation. If it is I plus 1, you have gained something. If it is L, you have not lost anything. All right, you lost something which was to be lost in any case. In fact, this can be made little more clever, that somehow here you try to guess the outcome of the branch. Okay, this is called branch prediction, and you try to do, since you are doing something in anticipation, why not make little extra effort and try to predict whether I plus 1 is the most likely consequence or L. So you somehow do that prediction and try to start one of the two. Again, there is a possibility that you may, since after all it is a prediction, unless the numbers get compared and you know finally whether it is true or false, you may not have made the right decision. So, but in case you have made the right decision, you have gained. In case you have not, you have lost something which you would have probably lost even otherwise. So, branch prediction is it's a I have stated in very simple term, but there are many issues involved, many ways of doing it. It can be done statically, dynamically, and to do it dynamically would require a lot of hardware support and so on. So, we will probably look at that little more in detail, but at the moment what we notice is that branch potentially causes these stalls in the pipeline. Okay, so I have discussed the basic ideas of a pipeline design. We began by looking at the relationship between a single cycle design and multi-cycle design, and then bringing pipeline design into the same framework and seeing how they compare in terms of clock period and CPI. So, we have seen that pipelining approach gives you fast clock similar to multi-cycle design and low CPI similar to single cycle design. Pipeline data path is obtained by introducing registers in between the stages in the forward paths. For analysis purpose, we had a symbolic representation which tries to show various instructions time wise or stage wise. And finally, we talked about 3 different types of hazards: structural hazards, data hazards, and control hazards. We have seen that in the simplified case we are talking of, it has been possible to remove structural hazards altogether. Data hazards also we can actually cut down to quite some extent by using forwarding. The control hazards are most nasty among these. We can do something about these, but not get rid of them fully. So, in subsequent lectures we will see more details about the design, the data path aspects, and the control. Thank you.